15? 15. Where's 15? Nope, that's 9. Oh, no. Oh! Ben Franklin! Alright, let's check this out. I haven't looked at this question in years. In 1751, Ben Franklin predicted the U.S. population would increase with a growth constant of K equals that. I have no idea if this problem is true, by the way, and I wonder how Franklin calculated this, if it is. But anyway, according to the census, the U.S. population was 5 million in 1800 and 76 million in 1900. Assuming logistic growth with K equals 0.028, find the predicted carrying capacity for the U.S. population. And it said hence use equation 3 and 4. Did I actually do that first? Yeah, it looks like I did, right? Okay. So that's my first step, is this. Honestly, I don't know what equations 3 and 4 are, but starting with this version, and remember this one is the version that the book uses, so I just went with that. So I'm manipulating it to get here to what the book suggested to do. So any questions just getting to this, this point? Okay, so then how can we use this? So it says, basically from the problem in the above, so if we let 1800 be time t equals 0, so that's the starting point, and then p in millions, so that means the starting population is 5. And we're using this growth constant, so let's, and then we also know 100 years later that we were at 76 million. So I'm just basically plugging all that stuff in to find out the carrying capacity. And then, what were we actually trying to find now? So find the predicted carrying capacity. Oh, okay, so that's it. Then I'm just solving for A. So any questions on that? And was this the U.S.? Yeah, carrying capacity for the U.S. So 943 million carrying capacity for the U.S. Anybody know what the population of the U.S. is right now? About? Yeah, I think it's like 334 million, something like that. We got a ways to go, huh? He thinks we could almost be like 3 times as much. Oh my God. Can you imagine that? I suppose if you were to take all of the... There's still a lot of land. There's still a lot of... not highly dense. So what loosely dense? Lowly dense? I don't know. Anyway, there's a lot of places where the density is pretty low. So, oh, there we go. Fun fact. Look at that. I looked it up. That's when I did this problem, apparently, was in 2017. Any other questions? Going once. Going twice. Joshua.
There's a problem that there's a unit called years instead of -1. What does that mean?
It's basically, and we do that a lot. You'll see that a lot with the constants, that K value. It's to make the units work out, basically, in the problem. Doesn't really have a meaning necessarily, just makes the units work out. Any other questions? Let me have your homework then, and we will take our celebration of knowledge, so I shall stop the recording now. Boom! There's number 1. Any questions about number 1? Where number 1? I say it every time, I don't know why. Any questions over that? So I could give you something like this on our celebration next week that can be done by hand. So I haven't decided yet.
Are we allowed to have calculators?
That's what I haven't decided yet. I'm thinking not. Because there's really nothing else we need them for. I guess. It depends on what I have you do with the other, with like, I don't know. I'll let you know. Anybody want more time looking at this before we look at number 2? Okay, here's number 2. Don't forget, it's not quite in the form yet to look at a carrying capacity. That has to be a 1. So you have to factor out the 2 first, and then you can just look at it to find the carrying capacity. A little sneaky trick. By the way, this was an actual question on an AP exam a few years. I don't remember what year. I know! So, yep, watch out for that. Hopefully, though, at least you saw that it would be the carrying capacity. Very important. Any questions about that? Ready for number 3? Alrighty. Hey, yeah. I don't know about, like, what I did. I mean, because there's so many different ways of doing this. I just looked, okay, well, y is 0. The slope is going to be -1. Let's see if I can start eliminating at least and look like along the x-axis where y is 0. Which ones don't have a slope of -1, and I'll eliminate those. But then it turned out this one didn't, and this one didn't, and this one didn't, and this one didn't, and only this one did, and yeah! So that's all I needed. Process of elimination, baby. Any questions at all on the reality check? So exciting. Well, then you know what time it is. Yep. Notes time. No, not nap time. Wrong N-word. Oh my gosh, how many of you guys are playing Wordle?
Oh, Wordle!
So much fun, isn't it? So, I have to admit, so there's another one called Wordmaster. So if you like Wordle, but you're like, dang, I wish there was more than one a day. Wordmaster. It's a Wordle ripoff, but you can do unlimited every day. So that's what I spent entirely too much time this weekend doing. But it was fun. Okie dokie, so our topic for today are first order linear differential equations. This is not a topic for the AP exam, but I still like it, so we're doing it. Damn it. All right, so first thing we're going to do is, what the heck is a first order linear differential equation? Well, I'm glad you asked. Let's look at a definition. What, you didn't ask, you say? I don't care. Definition. Eek. First order linear, wish these had a shorter name though. Differential, oh my god. This would be a good hangman. Actually, the longer hangmans are usually not they're like the easier ones because there's so many letters. First order linear differential equations are of the form. Dun dun dun. dy dx plus p of xy equals q of x. Dun, dun. Oh, yes?
Can we just call them fold with an E on the end?
Fold?
Fold in.
Fold. Oh, yeah. I like it. Okay.
But
So in this class, yes, we can call them fold. Foldy.
it's not an AP test.
But, you know, if you're in another math class, don't call them foldy because they probably won't know what you're talking about.
They don't know exactly.
So foldies. Yes, I like it. This is called the standard form right here. And just to finish this up, where P and Q, mind your P's and Q's, are continuous functions of X. Dun, dun, dun. This definitely is cloud-worthy. Anybody know where that expression comes from, mind your P's and Q's? Really? Oh, I guess now I'm dating myself. Mind your P's and Q's. Mind your business. Mind your P's and Q's. Mind your... I don't know. I don't know where P's and Q's are. Or maybe it's because P's and Q's, when you write them, the lowercase letters, they look so similar. You have to pay attention. What does that have to do with minding your own business? I don't know. I'll look it up later. See, it's not just a math class here. Okay, so let's look at how you solve these bad boys. Because if you look at it, we're not going to be able to solve it by separation of variables. Oh, yes.
So just to make sure, in a first order equation, you can't have a function of y.
I don't know what you mean.
Like when we have x's in there, you have like a y that's multiplied to it, but you don't have anything.
Exactly. Yeah. So this term right here will be some function of x times y. In fact, if this term is only y, p of x would be 1. But you do have to have the y times some function of x. But you're right, only functions of x. Okay, so to solve these things, let's go blue. To solve a foldy. To solve a foldy. It's just fun to say now. So first, write it in standard form if it's not already, so that you can identify your P and Q. Write the equation in standard form to identify P of x and Q of x. See? Even he says so. Oh my goodness. So when you're writing it in standard form, the thing to focus on is the dy dx should be by itself. And then there should be another term with just a y in it. But, I mean, the ones we're going to be dealing with, either they're already in standard form or you just move a term to the other side and you're magically in standard form. But in case they're ever kind of wonky, focus on getting the dy dx in a term by itself. And then it kind of falls into place. All right, so we got that. Once you write it in standard form and you find your P and Q, then you have to find what's called the integrating factor. And I will explain this in a moment, but just write it down. Then you find the integrating factor, which for these is going to be u of x, which is equal to e to the power of the integral of p of x dx. So yes, we have an integral and an exponent. I used to work with a guy that was obsessed with matrices as exponents. It was actually pretty fascinating, but that was his pet project. The first job I had actually was really cool because it was a nonprofit that had a contract with the school district to teach. But one of the things that this nonprofit stressed was keeping math skills of the teachers current and fresh and, you know, all that. Like, if you only teach Algebra 1, you're going to forget all the stuff you learned in the higher levels of math. So every week we had to do a workshop, a math workshop. And it was just, you know, we put it on for ourselves. Somebody was signed up, hey, I'm looking at this topic. This is pretty cool. And we just talk about it with everybody. Anyway, it was really cool. So every time he signed up, it was always matrices as exponents. Oh, Harold speaking today. Matrices as exponents. All right. I wish I could remember. I remember it had something to do with E and I. Matrices as exponents. But I forget what. Anyway. All right. So once you do this, then there's a formula for finding the general solution. So the general solution is y equals 1 over u of x, and then in parentheses, times the integral of q of x times u of x dx plus c. And yes, it may seem weird right now, that plus c, but again, go with it. I'm getting there. And so, yeah, then we got that. So let me explain this integrating factor, which in the explanation then will explain this plus c that's going on there. So, let's think about it. Oh my God, we got to think about it. I hate thinking. Thinking hurts. Nah, thinking's good. Okay, so let's just start with a folding. I like this, thank you. Start with a first order linear differential equation. dy dx equals p of x. Oh, wait, not equals. Plus p of x y equals q of x. So let's see what happens when we multiply both sides of this equation by that integrating factor. Multiply both sides by the integrating factor. U of x equals e to the integral of p of x dx. All right. So if we do, it's going to distribute to both terms on the left and be multiplied by on the right. So we have dy dx times e, and it'll help here. You may be thinking just write it out as u of x. I'm actually going to write it out as the e to the power of, because I want us to see something. So anyway, we have that plus p of x y e, the integral p of x dx equals q of x times e to the integral of p of x dx. Now there's something that's probably not obvious, but when it's pointed out, hopefully we'll see it. There is a nice thing happening on the left-hand side of the equation. And that is the derivative of a product, if you use product rule. So which one, you may ask? Well, that is the derivative of y e to the integral of p of x dx. So let's chew on that for a moment. Remember, if you use product rule, so you got derivative of, that doesn't work, derivative of the first times the second. That works, there's the first term. Plus first, which is right there, times derivative of the second. And remember, to take the derivative of e to any power, it's e to that power times the derivative of that power. So it works. So does that make sense? Why this whole mess right there is the derivative of this? So then, we can integrate both sides. This is why it's called the integrating factor. It turns it into something that we can integrate to get the y by itself. So if we were to integrate both sides, that would cancel out the d dx. So we have y e to the integral of p of x dx. And then we have the integral of the right-hand side but I'm integrating both sides. So I do have, whoops, need a dx here. We will have a plus c there when we integrate. And then now for the final step, I'm going to go ahead and just get the y by itself. But when I divide by e to the power of the integral of p of x dx, that's just dividing by u of x. So I'm going to change it to u of x. So y is 1 over u of x times the integral of q of x u of x dx plus c. Ta-da! And there we go. Yes, Sid?
Why do we have the plus c, the integral expression is like the indefinite integral thing is still there?
So the important thing is, and you'll see it when we do an example, so when we integrate this side, it's going to have its own plus c that we get, and that c would then have to integrate, or sorry, would have to multiply by 1 over u of x.
So the c you get from integrating that is not the same as that c.
Which c's are we talking about?
Okay, so we have the integral of qx times e is the integral of that thing, right? So if we integrate that, we'll get some, because it's an indefinite integral, we'll get some expression plus its own c, right? And then that's different from the plus c that you wrote on the side.
Actually, no, it's really going to be the same c. But the c here is to show, it's to remind us. Let's do an example and I'll come back to that because it might make more sense when we do an example. If not, let me know. So yeah. So there's a couple of things here that I do want to point out. Let's actually, for purposes of our notes, let's make a little note here. So if you're looking back at this, this is really think product rule of derivatives. And then there's another thing that I'm going to write out, and this will come up and you'll see it. But so right here when we're multiplying both sides by u of x, if you just look at it, so first I'll explain it and then we'll write it in words off to the side. But this is e to some power. Now, when you're doing this integral, it doesn't always happen, but if it happens, like let's say that this integral ends up being something with a natural log. So let's say that you were integrating 1 over x. Well, we know that the integral of 1 over x is the natural log of the absolute value of x. So this would be e to the power of the natural log of the absolute value of x. But then the e and the natural log cancel out, so it ends up just being the absolute value of x. Are you following me so far? But you're going to see that when we do this, we just seem to drop the absolute value for some reason. How can we just do that? Well, the reason why we can just do that is because think about what the purpose that the u of x is serving here. The u of x gets multiplied by both sides of the equation. So it doesn't matter if u of x is positive or negative, you're going to get the same resulting equation. So rather than saying the absolute value of x, which would then force u of x to be like plus or minus x, we just drop the negative. We just drop the absolute value and don't even worry about it because it's the same darn thing either way. So it may seem as when you were doing the work that, wait, just dropping the absolute value. I guess you just didn't want to deal with it, which is kind of true because we didn't have to. So does that make sense? Maybe it'll make sense when we go through an example too. But let's just put a little note. Whoops, a little note here about that. A note about u of x. So if u of x ends up being the absolute value of something, then u of x would be the plus or minus of that. But we are multiplying both sides of the equation by u of x. So it doesn't matter. I can't spell matter. Doesn't matter if u of x is positive or negative. So, for convenience, we just use u of x would be x, or whatever the thing is in the absolute value. Just drop the absolute value, we don't need it. I don't think that doing an example is really going to explain that any better, because we aren't going to go through the steps that I have here. We're just going to jump right to the final general form. So remember, the key is well, if you have the left-hand side equal the right-hand side, and you multiply by a negative on both sides, you get negative left-hand side equals negative right-hand side. But then you can just multiply both sides by a -1 and get back to left-hand side equals right-hand side. It doesn't matter if you multiply both sides by a positive something or the negative of that same thing. It's the same thing. So any questions about that? Okay, let's do an example. Anybody still need this though? Because that's the end of the notes part, so now let's do it. We're going to do this one together. So this is for the notes that I post. I have the solutions on the next page. That way people at home can pause the video now and try it on your own. Yay! Anyway. So the key is follow those steps that I gave you. You're going to put it in standard form. You're going to find p of x and q of x. And actually, I like to find u of x at the same time. And then I just plug into that formula that I gave you. So let's do this one together. First of all, do I have to do anything to this, do you think, to put it in standard form? Yeah, it's already in standard form. Very good. So I'm just going to write it out. Ooh, I don't want to write in red, though. Red, it hurts our self-esteem, they say. Oh, I keep doing that. I keep putting plus sign or equal signs instead of plus signs. All right, so we got this. So can you guys tell me what p of x is?
1.
Excellent. Can you tell me what q of x is? Excellent. And then u of x, according to our formula, is e to the integral of p of x dx. So in this case, what is it? Just e to the x. We don't have that absolute value here, so, I mean, that comment above is irrelevant here. Sid, yeah?
And this one not become like a e to the x plus c and then e to the x.
Yeah, it's just e to the x. All right, so now we plug into the formula. Just, you know, whenever you're learning a new formula, it's always good practice when you're trying to memorize it. When you're working it out in problems, every single time, write out the original formula so you can plug in. The more you write it out, the easier it's going to be to remember. So let's write it out. Whoop, stop it. So y equals 1 over u of x times the integral of q of x, u of x dx plus c. And then we'll just plug in. So y is, you can write 1 over e to the x. You can write it as e to the negative x if you don't like fractions. Whatever. Whatever. Q of x is e to the x. Oh, u of x is also e to the x. How the heck do we integrate e to the x times e to the x? Oh, yeah. Remember, you can just rewrite it as e to the 2x. And then you can integrate it. So y is equal to 1/2 e to the 2x. So this plus c really is coming from the integral, but you usually see it written out in the formula to make it very clear that that c is not just a plus c that's tacked on to the end of the entire equation. It's just tacked on to the end of the integral because, so first of all, when I multiply e to the negative x times e to the 2x, that's just e to the x. I'm distributing now. That c will get multiplied by the e to the negative x as well. It's the only reason why it's written out there. Just to remind you to multiply it also by the u of x. Or 1 over u of x. There you go. That's it. Very exciting stuff, eh? I know. So, it's really as difficult as it is to integrate p of x. And then q of x, u of x. Other than that, not so bad. Ready to try one on your own? Of course you are. Try this. So for you at home, go ahead and try this on your own as well. Pause the video now. All right. Anybody one more time after you find u of x? It was just plugging into the formula. Any questions here? So, of course, the integrand just changes to 1 over x. So, kind of what we were talking about, a lot of times I'll leave it off until I integrate. It'll magically appear on the next step. Sorry, because it's really the c from the integral. Alrighty, see, look, it magically appeared. They're magically delicious. Now, one thing I do want to point out is, notice I do have the absolute value here. And that is because this is not coming from u of x that we're multiplying on both sides. If u of x was the absolute value of something, we could leave it off. Because that's a thing that you multiply by both sides of the equation. This is just from the integral of that, which we're not multiplying by both sides of the equation, so I do need the absolute value there. There is our answer. Does that make sense why this one I do need the absolute value? Okay. Any questions? So I have one more of these and then a word problem. Do you feel like you got this pretty good, just the process, or do you want to jump to the word problem, or you want to do one more of these first? Just jump to the word problem? All right. If you feel like going to do it, you can look at the notes and you'll see that there's another one to try. And yeah, there's a solution all worked out. All right, here's a word problem. You guys wanted it. All right, let's look at this together. And again, it's one of those that you can write down as much or as little of it as you want. You do have something similar to this on your homework, just saying. Oh my God! They're gonna make us think on the homework. All right, a tank contains 50 gallons of a solution composed of 90% water and 10% alcohol. Remember mixture problems? A second solution containing 50% water and 50% alcohol is added to the tank at 4 gallons per minute. Ooh, that sounds like a rate or a derivative. As the second solution is being added, the tank is being drained at a rate of 5 gallons per minute. Assuming the solution in the tank is stirred constantly, how much alcohol is in the tank after 10 minutes? You may be wondering, when would we ever have a first order linear differential equation? I believe there's going to be one that appears here. Or I just did it for fun. It has nothing to do with folding problems. Shall we work on this together? I'll tell you what, actually, I think it'll be more beneficial if you first, I'm going to give you guys like 4 or 5 minutes to just see what you can wrap your brain around on this problem, and then we'll look at it together. I don't expect you guys to solve this in the 4 to 5 minutes, but I think if you chew on it first before we do it together, you'll have more to stand on when we're doing it together. So, I'm got my watch on. We're timing it. I'm going to pause the video. So hopefully now you've just kind of, I mean, even if you didn't get anywhere, you've kind of got it in your head what's happening in the problem. So we're starting off with 50 gallons of a solution. That's one ratio of alcohol to solution. And then we're adding in another solution of a different ratio. And that's being added at one rate, and then it's also being removed at a different rate. So what the heck? So let's first define some stuff here. So since the answer wants to know how much alcohol is in the tank after 10 minutes, maybe if we let our function y of t equal the amount of alcohol in the tank at time t. So if we let y equal that, then what does y prime of t represent? Let's be more specific. What do you mean the rate of change of it? How does alcohol change? It's not the rate of change. I mean, I know what you mean, but I want to be very specific. Yes. The amount the rate, oh my God, the rate of change of the amount of alcohol with respect to time. Okay, so we got that. So let's come up with an expression, even if it's just in words and not in math yet, that represents the rate of change of the amount of alcohol. Because the thing that the reason why I wanted to be very specific about this, what this rate of change is because in the problem, we're actually given 2 rates. We know that solution is being added at 4 gallons per minute. That's a rate of change. And then we know it's also being removed at a rate of 5 gallons per minute. That's another rate of change. But those are different rates of change. They are not the rate of change of the amount of alcohol They're the rate of change of the amount of solution. We're going to have to play around with those rates. But y prime of t, one way, I mean, we obviously have alcohol being added and alcohol being removed. So let's see if we can figure out the rate at which the alcohol is being added and the rate at which it's being removed. And that, when we subtract them, that's going to give us the rate of change of the amount of alcohol. So what I mean by that is this. That means that y prime of t is... Now I'm going to be a little loose here, but it's the rate of change of the amount of alcohol in. So I'm just going to say rate of change of the alcohol in minus the rate of change of the amount of alcohol out. So does that make sense? Because now we just have to figure out how to change each one of those into math speak. This is where we can use dimensional analysis to help us out too if we need. Ooh, dimensional analysis. All right. So, y prime of t. Rate of change of alcohol in. The amount of alcohol in. Anybody have an idea? Greg.
2 gallons per minute.
How did you get that?
Because if the added is 50% alcohol, 50% water, so if the total solution is 4 gallons per minute, half of that would be 2 gallons of alcohol per minute.
Exactly. So I'm going to go ahead and, I mean, this one's easy to see. It's just 2 gallons. But I'm going to go ahead and write it out with exactly what Greg said. We know that solution is being added at a rate of 4 gallons per minute. So we have 4 gallons of solution per minute coming in. And it's that solution has a ratio that's 50% alcohol. And so you can write this however you want. But that means we have the ratio, the proportion of alcohol to solution is 1 gallon of alcohol for every 2 gallons of solution. Or like I said, however you want to write that. You want to write it 0.5 over 1, however. It's still just, you're multiplying by half. And that's going to give us, when the gallons of solution cancel out, that's going to give us the 2 gallons of alcohol every minute coming in. So does that make sense there? So that's 2. Ugh. So we're going to have to think about the same thing for going out. This is where it gets a little more complicated thinking, though. We do know that the amount of solution being drained from the tank every minute, that's what, 5? Is that what it said? Yeah. So we have 5 gallons of solution every minute that's being drained. 5 gallons of solution every minute being drained. I may need to move this over a little bit. So what we need to do, same kind of thing here. This is just where it gets a little trickier to think about. We need to figure out what the ratio of alcohol to solution is that this 5 gallons is made out of. Well, okay, let's say it again. It's actually going to be, it'll vary. Yeah. And the reason it's going to vary is because we started off with this stuff here, and then it's going to change. It's the ratio is going to change based on, because the more and more we put in, the more alcohol, like the more concentrated the alcohol is going to get. So that's why it's not a fixed proportion. But we do have Y that represents the amount of alcohol at any given time t. So we have Y gallons of alcohol at time t. So now we just need to figure out how much solution we have at time t. Yes? Where are you getting the 5 plus 2t? You're on the right track, but it won't be that. First of all, we have 50 initial gallons. Because we're not actually... Oh, sorry. It's not... I can't speak. We want gallons of solution at time t because we want the gallons of solution to cancel out. So don't think about alcohol. Think about how much solution. So we're starting off with 50, so we are going to take that starting amount. But every minute, we're adding 4t gallons, but we're also removing 5t gallons. We add, every minute we add 4 gallons and remove 5 gallons. So yes, I can just make that 50 minus t. So my equation for y prime is just 2 minus 5 over 50 minus t y. So take a minute to chew on that if you need to. Does that make sense? Yes, Joshua. Okay. Any other questions where this comes from? Because now we're kind of on the home stretch. Look at this. We're just going to solve this. Is this a first order linear differential equation? Is it in standard form? No, but all we have to do is move a term. It'll be in standard form. Y prime of t plus 5 over 50 minus t. There's our p of x times y equals q of x. Dun, dun, dun. So then you would just solve it. I won't make you guys go through that unless you want. I'll let you choose. Wait a minute. Where did I, what? What? Okay. So then we go ahead and solve this, but we're not going to find a general solution. We're going to find a particular solution, which means we're going to have to find C. And then you just plug in 10, because it wanted to know how much alcohol is in the tank after 10 minutes. So the last question that I will make you guys do, and then I'll just make the solving it optional if you want. How are we going to find C? So once we go through the whole thing that you guys did on the previous 2 problems of, finding u of x and doing all that good stuff, and you get y equals blah, 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 blah. There's a C in there. How are we going to find C? Yes. Where'd you get this 5 from? Is that from the amount of gallon, the rate of change of leaving the tank?
No, it's just the initial value.
Oh, exactly. Use an initial value. We haven't used this yet. We're starting off with 50 gallons. That is 10% alcohol. So at time t equals 0, you have 10% of 50. You have 5 gallons of alcohol. So I'm just going to put a little note here. You're going to solve this foldy and use y of 0 equals 5 to find C. Now you got the particular solution, then you just plug in 10. Hey! Any questions about that? So I will leave it optional, but it'd be, I don't know, kind of nice if you guys tried this. But if you want to jump right to your homework instead, that's okay. Feel like you got a good handle on it. But I will go ahead and show you the solution in a moment if you're curious. So for those of you watching this video at home, give it a go. Otherwise, this is the end of the video. Bye. I'll scroll through the solutions so you can see it. Okay, that's the end.